Hello everyone, I'm Wei Song from Nanjing University of Science and Technology, China. Today I'm glad to present our work, PermDroid, automatically testing permission-related behavior of Android applications. This is the outline of our presentation. Let me first introduce the background of our work. Since API level 23, Android adopts the runtime permission model, which allows users to revoke or grant permissions at any time through the system settings. The Android runtime permission model introduces challenges for app testing. The app developers should guarantee that the apps can always behave properly under different permission configurations. However, testing the apps under all permission combinations is time-consuming because the combinations are explosive when the apps require several dangerous permissions or permission groups. For example, Alipay applies for 7 dangerous permissions with a total of 128 combinations. If for each permission combination the testing takes half an hour, a total of 56 hours will be needed. And for Facebook, it applies for 8 dangerous permissions, which requires more time for app testing. In app testing, especially regression testing, many aspects tests can be conducted in parallel, and every aspect is not expected to last too long. So, an efficient approach should be pursued to make sure that permission-related behavior testing is not the foot dragger. Our studied problem in this paper can be formalized as follows. How to automatically, systematically, and efficiently test the permission-related behavior of Android apps. Before introducing our approach, let us review the state of the art. Most of the existing work focuses on app GUI testing. Unfortunately, these general GUI testing tools are not permission aware, as they do not consider the runtime permission model. PermDroid is the only work which considers the runtime permission model in app testing. Given a test case of the app, PermDroid first identifies the permissions related to this test case and then rerun the test cases repeatedly, and each time uses a different combination of the identified permissions. However, if the app is not private with test cases or the test cases are irrelevant to permissions, this tool is of limited help. So to this end, we present our approach, PermDroid. Our main idea is lies in that we observe that some functionalities of apps are only related to specific permission configurations, regardless of whether the other permissions are granted or revoked. Therefore, when some functionalities of an app are tested, only the combination of the relevant permissions need to be considered. Thus, we can reduce the number of testing iterations from exhaustive to locally exhaustive. This figure gives the framework of PermDroid. It takes in an APK file as the input and tries to output the crash reports and target statement coverage as the output. It tries to find the permission-related bugs in this app. It consists of 2 important modules: a static analyzer and a dynamic explorer. In the following, I will introduce these two modules to you. In the static analyzer, we have two. First, localize the target API call sites. To facilitate dynamic exploration, in the static analysis phase, the permission and the location information of all permission-related API invocations need to be determined. We consider the target APIs include the following two kinds. The first one is a common permission-related APIs. For example, check self-permission. For this kind of permission-related APIs, we should determine the permissions behind these APIs from data flow analysis. And the second kind is APIs that requires specific properties, permissions. For example, those shown below. There list three APIs that requires the camera permission. For this kind of APIs, the permissions required is obtained from the API to permission mapping. And another important work done in static analyzer is a construction of STG. A state transition graph (STG) of the APP is constructed to guide the subsequent dynamic exploration. This figure just shows, just illustrates STG of an APP. It just captures the jump information between different kind of activities of the APP. Secondly, we want to introduce the dynamic explorer. In the dynamic explorer, we conducted an permission-directed exploration. Because based on the STG, we can iteratively test the target activity states until all permission-related API invocations are fully tested under the combination of the relevant permissions. We changed the permission configurations at runtime with the help of ADB command. And in the dynamic explorer, we implement some monitors. The first one is called a runtime monitor. It just monitors the APP execution. And the second one is error monitor. It just monitors the error information if the APP have bugs. And the last one is the coverage monitor. It just monitors the target API invocations. It just indicates whether some API invocations are executed. From this monitor, we can calculate the coverage information after testing. Finally, we will introduce the evaluation of PermDroid. To this end, we want to answer the following three research questions. RQ1, target statement coverage. RQ2, bug detection ability. RQ3, testing efficiency. To this end, we have to select some APPs to constitute the benchmark. We have the following selection criteria for the benchmark selection. First, we randomly select a variety of popular APPs. Second, the target SDK version of the APP is at least 23. Third, at least one dangerous permission in the Android manifest file is declared. Under this selection criteria, we have selected 40 open source APPs from F-Droid and 10 commercial APPs from Google Play. So totally 50 real-world APPs are used. And in the evaluation, we aim to compare our approach, PermDroid, with the state-of-the-art testing tools, that is Monkey, APE, Jetstar. In addition, we also compare PermDroid with three baseline strategies, which considers permission configurations. These strategies we consider include or and none, pairwise, and exhaustive. Let me first report on the experimental results of RQ1, targeted statement coverage. Compared with the state-of-the-art general testing tools, PermDroid achieves a higher permission-related API invocation coverage, and it improves 16% to 30% API invocation coverage. And compared with the baseline permission-aware strategies, the permission-related API invocation coverage of PermDroid is higher than that of all and none and pairwise, only a little bit lower than that of exhaustive. PermDroid totally uncovers 7 permission-related bugs, while the other 3 general testing tools together discover only 1. The 7 permission-related bugs PermDroid detects are shown in the finger. We can see two of them have been confirmed by the developers. Lastly, we want to report on the testing efficiency. Compared with the state-of-the-art general testing tools, PermDroid can quickly achieve the higher permission-related API invocation coverage than that of the other approaches, as illustrated in this figure. And also compared with the baseline permission-aware strategies, PermDroid is more efficient because it only tests the APPs one time, while the exhaustive approach will test the APPs several times, and each time it needs to manually change the permission configurations. For example, the average testing time of PermDroid is about 10 minutes, whereas the exhaustive strategy takes about 15 minutes to test an APP. In summary, first, in this paper, we have first show you the necessity to test APPs under different permission configurations, and to improve the testing efficiency, we have present PermDroid, which just utilized a locally exhaustive strategy to test APPs. And the experimental results show that our approach, PermDroid, can achieve a higher statement coverage and can find effectively found bugs in real-world APPs. Okay, thank you very much for your attention. The artifacts of our work can be found from the following links. Thank you.